Hello everyone. In today's lecture, we are going to learn all about activation functions. The reason neural networks become so expressive and powerful is that they have these things called activation functions, which convert linearities into non-linearities and which basically allow us to capture a lot of interactions between the input features and to discover relationships between them. Activation functions are one of the fundamental building blocks of neural networks, which help us to uncover complex relationships between the input and the output data. Today's entire lecture is devoted to understanding the different activation functions, how they work, what are the advantages, disadvantages, and which activation function should you use for a given machine learning problem. Interviewers tend to ask a lot of questions related to activation functions in interviews. So it is very important to have your concepts clear regarding the same. So let's get started. Uh, Before we start, I just want to give a quick recap of the neural network structure and where out activation functions actually fit in. So here I have shown two hidden layers in this neural network. There is an input layer with three different inputs, and there is an output layer. In the output layer we have one output. Okay, so in each of these layers, in the first layer there will be the weight matrix w1, in the second layer there will be the weight matrix w2, in the third layer there will be the weight matrix w3, and you can see all of these different neurons which have been arranged here in the different layers. So this same neural network can also be written in a block representation as I've written below. So first you get the input x, it goes through the first set of weights and biases. Then we get z1, which is just the linear summation. So w1 transpose x plus w01. Then z1 goes through an activation function. So basically every single neuron here will have an activation function. And then when the activation function applies on Z1, it leads to the output of that layer, which is called as A1. So in the first layer, for example, every single neuron will have an activation function and an output corresponding to it. And all these outputs of different neurons will feed in as inputs to the next layer. So here you can see the input to the next layer is called as A1. Then it will go through a set of weights W2 and W02. It will go through the activation function of the neurons in the second layer. Then it will produce an output A2. And then it will go through W3, W03. We will go through the activation function of the last neuron. And then finally we'll get the output A3. Okay. So this is the building block representation of the neural network here. And if you were to represent the output in terms of just the functions, this is what the output would look like. Here I've used the sigmoid activation function. W3, W2, and W1 are the weights, and W0, W02, and W03 are the biases. So essentially, this is similar to y equal to f of x, where f is this huge function which we have, sigma of sigma of sigma. It will be useful to keep this functional representation in mind as we understand the properties of different activation functions. Sometimes it's a bit harder for us to think in terms of building blocks, but it's easier to think in terms of functions. So keep this formulation in mind. Remember that a neural network is just a big function at the end of it, a function which looks like this, which is a bit more complex. So this is way complex than a single sigmoid, right? It's sigmoid of sigmoid of sigmoid. All neural networks can essentially be represented in huge functional forms like this. Now that we have this in mind, let us look at the level of a single neuron. Every single neuron has three functions. It does the summation operation on the weights, it adds the bias term, and then it applies an activation function. So this is the activation function f, which is applied on w1 x1 plus w2 x2 plus w3 x3 plus b. W's are the weights which are feeding into these neurons based on the inputs. So this is x1, x2, x3, and then every input will have a weight w1, w2, w3. and then there will also be a bias term. So every single neuron which has been shown here, these neurons in the first hidden layer, these neurons in the second hidden layer, and this neuron in the output layer, all of these neurons do these three functions. They do a summation operation, they add a bias term, and then they apply the activation function to the resulting output. So activation functions show up wherever neurons show up, and they play a fundamental role in not only the forward pass but also in the backward pass when we do the gradient with respect to uh, the weights, since we want to optimize the weights. So let us see the different activation functions and how they compare and contrast with each other, and let's see their advantages as well as disadvantages. All right. So let's start looking at the types of activation functions which are commonly used in machine learning. The first activation function which we are going to look at is the sigmoid. We have covered this a lot in previous lectures. So the sigmoid activation function looks like this. Y is equal to 1 upon 1 plus e raised to minus x. And if you plot this activation function, it will look something like this. So this activation function it always returns a positive value. It is capped at 1, so it never becomes higher than 1. It always lies between 0 and 1, and its value at 0 is zero point 0.5 x and y. So this is the sigmoid activation function, and it's typically routinely used in binary classification. So remember that since the sigmoid always takes values between 0 and 1, the output of the sigmoid function is very commonly treated as probability. So if you want to distinguish between two categories, like whether it's a cat or whether it's a dog, you can treat the output of the sigmoid as that probability, and then you can say that if it's greater than zero point 0.5 it's a cat, if it is less than zero point 0.5 it's a dog. So sigmoid activation function is typically used in such kind of binary classification problems where we have to assign probabilities to the two classes. We have to assign probability to, let's say, what's the probability that the neural network is classifying this as a cat, what's the probability that the neural network is classifying this as a dog. So now let us look at the advantages and the disadvantages of this particular sigmoid. So the first advantage is that, so let me write this down. So first advantage is that it always belongs between 0 and 1. So the output belongs between 0 and 1, and it is linked to probabilities. So it's a very good function to be used for binary classification. It's a very good activation function to be typically used for binary classification. That's the first advantage of the sigmoid activation function. The second advantage is that this function is smooth, which means that it is differentiable at all the points at it is differentiable for all the inputs or for all x. This will be very useful for us because remember, when we do the backward pass we have to take the derivatives, right? So we need to make sure that the activation functions are also differentiable. So one advantage of sigmoid is that it's pretty smooth, as you can see from the graph here. So it's continuous and differentiable at all the points. Okay. Now let us come to the biggest disadvantage of the sigmoid activation function. And to really understand the disadvantage, I want to use this functional form. So remember, if a sigmoid activation function is used, let's say in a neural network, the final y will look like something like this: sigma of W3 transpose, then sigma of W2 transpose, then sigma of W1 transpose X plus W01 plus W02 plus W03. It will look like this, remember. And now what we want to do is we want to find the derivatives, okay? So the loss will look something like y minus the actual whole square. So now if we want to take the derivative of the loss with respect to weight, it will look something like 2 into y minus a multiplied by the derivative of this whole thing, dy by dw. So ultimately, we will need to take the derivative of this entire quantity with respect to w, correct? Now let's see what that would look like. If you want to take the derivative of this quantity, let's say with respect to w1, you will need to apply chain rule multiple times. So first you will have sigma dash of this entire thing, then you will multiply it by W3, then you will take the sigma dash of whatever is remaining, then you will multiply it by W2, and then finally you will take the sigma dash of the innermost sigmoid. When I say sigma dash, I mean the derivative of the sigmoid function. So remember, at multiple times, we need to take the derivative of the sigmoid function. That's the first thing I want to tell you. The second thing is that if you look closely at the sigmoid function, it looks something like this. So try to look closely here. Let's say if the x value is too high. So let's say if we are taking the derivative of the sigmoid function, and if the x value is too high, uh, what I want you to see is that for very high x, the sigmoid is almost constant here. It almost looks like a flat line, right? And so this derivative will be equal to 0 for very high values of x. Similarly, if you look at very low values of x over here, the sigmoid looks like a flat line, right? So there is no change. So the derivative will be equal to 0. So now, if you look at finding the derivative of loss with respect to w, it will involve this derivative of y with respect to w. And that will involve finding the derivative of the sigmoid quantities 3 times. But if the x is very high, then this will be 0, this will be 0, and then this will be also 0. Which means that dy by dw will be 0, which means that derivative of the loss with respect to weights will be 0. And what will happen if the derivative of the loss with respect to weights is 0? Remember, in gradient descent, the way we update the weights is that w new is w old minus a step size times the derivative of the loss with respect to weight. So if this derivative itself is 0, which means our weights are not updating, and that's a huge problem for us. The main purpose of gradient descent and optimizing a neural network is to update the weights of the neural network so that the loss is minimized. But if the weights itself are not updating, then we are stuck. We are stuck at a during our optimization process at a very high loss, which means our neural network is not optimized and it won't reach close to the final answer. That's the main problem of the sigmoid function. If the input values are too high or too low, then the derivatives of the sigmoid function become 0. And since that is 0, it affects the derivative of the entire loss with respect to the weights. And that's why the weights don't update. And this problem is called as a vanishing gradient problem. Vanishing gradient. So this is very typically asked in interviews to explain the vanishing gradient problem. I always find it very helpful to explain it through this functional representation. It's very difficult to explain this problem through the block representation because it's quite difficult to understand how the sigmoid is related to the derivative of the loss function with respect to it. But if you write it in the functional format, here we can very clearly see that where the derivative of sigma actually comes into the picture in finding the derivative of loss with respect to the weights. So the vanishing gradient problem is one of the biggest problems or one of the biggest drawbacks of using a sigmoid. So just keep this in mind and don't just explain the vanishing gradient problem by saying that okay, the sigmoid stagnates and that's why derivatives become 0. Exactly show the interviewer when you take the gradient of the loss with respect to the weights, you do need to take the gradient of y with respect to w, and that involves taking the gradient of sigma many times. And since the gradient of sigma is 0 for high x or for low x, the loss stagnates and the weights are not updated. That's one of the major drawbacks of the sigmoid activation function, but it's typically very commonly used as the final layer in binary classification tasks. The second activation function, which is very common, is the tan h activation. And the functional form of tan h is y is equal to 2 upon 1 plus e raised to minus 2x minus 1. So this is the functional form of the tan h, and you can see that it kind of looks similar to the sigmoid activation function. Look at the functional form of the sigmoid. Here also there is e raised to minus x, but here there is 1 upon 1 plus e raised to minus 2x minus 1. Let us see what are the advantages of tan h over sigmoid. So if you plot the tan h activation function, right, the first thing you will notice is that it does not lie between 0 and 1, but rather the tan h activation function lies between 1 and minus 1. So it looks okay. Need to do a better job at the drawing here. So the tan h activation function actually looks something like this, and this is plus 1, and this is minus 1. So it's actually centered around 0. It lies between plus 1 and minus 1. And this is tan h of x. Now, what I want to show you is how it looks when we plot the sigmoid. So if you plot the sigmoid activation on top, it will actually look something like this. So this is the sigmoid of x, which we have already looked at in the earlier section. Okay, now can you try to think what are the advantages of the tan h activation function over the sigmoid activation function? There is a very big advantage of tan h, due to which tan h is actually preferred a lot compared to sigmoid these days. But first, I want you to pause the video and try to understand from these graphs whether you can predict the advantage of tan h over sigmoid. Okay, so this is the plot of the derivatives of the tan h with respect, and sorry, this is the plot of tan h with and sigma, right? Now let us plot the derivatives. So now I'm going to show you a plot of derivatives of tan h and sigma. So now we are going to plot derivatives of tan h and sigma. So this is also called as tan h dash, which is the derivative, and sigma dash. So let me plot this here and show you how it looks like. We'll use similar convention. We will use pink for tan h and we'll use green for sigmoid. Let me first plot the tan h. So the tan h derivative actually looks something like this. The maximum value which it takes is plus 1. And now let me plot the sigmoid derivative. The sigmoid derivative looks something like this. And the maximum value which the sigmoid derivative takes is actually just 0.25. So this is the derivative of tan h, which is also called tan h dash of x, and this is the derivative of sigmoid, which is also sigmoid dash of x. Now the main advantage of tan h over sigmoid is that the derivatives are much larger, and the derivatives take values between 0 and 1, whereas in sigmoid the derivatives are much smaller and they take values between 0 and 0.25. You can even see it from this graph. The derivative is the slope of the curve, right? So look at this particular slope, it's like this, whereas look at this particular slope of tan h, it's much higher. So the slope of tan h is much higher than the slope of sigmoid, especially near x equal to 0. And the reason it's better is that if you look at back propagation, as I showed you here, we have to take the derivatives of the activation function multiple times, right? So if the derivative is higher, it means that the back propagation is proceeding in a faster manner. Why? Because the updating the loss will happen faster. So if you look at the weight updates, the weight updates will be w new is equal to w old minus alpha times gradient, or the derivative of loss with respect to weights. And we know that this depends on the derivative of the activation function. So if the activation function is tan h, it will be tan h dash of x. If the activation function is sigmoid, it will be sigmoid of dash of x. So if it's tan h, we will see that tan h dash is much higher than sigmoid dash. And since the derivatives of tan h are higher, w will be nudged faster in the correct direction, which means that the computational time for tan h to arrive at the correct answer will be much lower than the computational time for sigmoid. Or in other words, using tanh as an activation function is much more computationally efficient than using sigmoid as an activation function, because the gradients of tanh are much higher than that of the sigmoid. This is the main reason why tanh activation function is preferred over sigmoid. But still remember that in the final layer, so here there are multiple layers of the neural network, right? So just let me write it here again. So let's say this is X, this is W01, sorry, this is W and W01. Then there is Z, then there's the first activation, then there is the output of the first layer, then there is the second set of weights, then there is the second activation, then there is output of second layer, then there is third set of weights, then there is the third activation, and finally we get the output of the final layer. Now remember that in the final output we have to make the classification of whether it's a cat or a dog. And so for the final layer, sigmoid is still preferred because it gives values between 0 and 1 which are directly related to probabilities. Remember, tanh gives values of -1 to 1, so it cannot be directly mapped to probabilities. So for all these other activation functions, tanh is generally preferred for classification tasks. Whereas if you just come to the final layer, then we still have to use the sigmoid, because in the final layer, the neural network has to make the prediction. So if the value is greater than zero point 0.5, it's a cat. If it's less than zero point 0.5, it's a dog. So these days, I have seen that machine learning practitioners use tanh in all the layers except for the final layer, especially for binary classification tasks. However, remember that the vanishing gradient problem which we saw before, tanh also kind of has that vanishing gradient problem because it also stagnates. So if you see high values of x, tanh also stagnates and becomes constant. If you see low values of x, tanh also stagnates and become constant. So this vanishing gradient problem which we saw, let me mark it over here also. So here also the derivatives become zero, and here also the derivatives become zero. So the vanishing gradient problem is still seen in tanh and sigmoid. One more advantage which tanh gives is that it's centered around zero. The sigmoid is non-centered, which means that it takes all positive values, but tanh takes positive as well as negative values, and that actually has an advantage in the training process. I have a separate section at the end of this video where I explain about centered activation functions versus non-centered activation functions. Tanh is a centered activation function, which means it has values from 0 to +1 as well as between 0 to -1. Sigmoid is a non-centered activation function because it's only positive, it only goes from 0 to +1, and that sometimes has disadvantages. And I have a separate section for that towards the end. Now, in the meanwhile, let us come to the third activation function, which will solve the problem of the vanishing gradient. And this is one of the most common activation functions which is used in machine learning these days, and it's called as ReLU. ReLU is also rectified linear unit, and the function for ReLU is very simple: y is equal to max 0, x. This also means that y is equal to x if x greater than 0, and y is equal to 0 if x is less than or equal to 0. And if you plot this, this is a very famous plot, and you must have seen it at many places because ReLU is one of the most preferred activation functions these days. So it's 0 all over here for negative values of x, and then it's equal to x for all positive values of x. So I'm just going to say this is x and this is y. So this is the ReLU activation function. First thing I want you to see is how it solves the vanishing gradient problem. This function never stagnates if x equal to positive. If x is positive, here you see how both these functions stagnated to constant values. But this function never stagnates. So it does not have the vanishing gradient problem, which is very good for us, which means that the weights will keep on updating and the loss will not get stuck if X is positive. Okay. So that's the main advantage of ReLU. That's why it's very commonly used in neural network tasks for regression. Um, so one major disadvantage of the rectified linear unit or ReLU is what happens when the input is negative. So look at this thing. What is happening when the input is negative? It's zero, right? And this is a big problem. The reason is because let's say we are in the middle of the training process, okay? And this is the neuron. The neuron has three things, correct? It has the summation, the bias, and the activation. So let's say it's a ReLU of W1 x1 plus W2 x2 plus W3 x3 plus B. Okay. And let's say there are these inputs x1, x2, x3, and W1, W2, and W3. Now, if it so happens that this summation is negative for some reason, if this summation is negative, then what will happen is that the output of this ReLU function will be equal to 0. And if the output of this ReLU function is equal to 0, it will affect every single thing, because let us look at again this thing. Let us look at this y, okay? And I'm going to write it here again because this will illustrate the problem to you much better. So let's say now my y is my ReLU times, instead of sigmoid, now we have ReLU, right? So W3 transpose, then ReLU of W2 transpose, then ReLU of W1 transpose, and things might be there inside. Okay. So the main thing to apply the chain rule now, if you want to find the gradient of loss with respect to the weights, or rather if you want to update the weights, then W is equal to W minus alpha times dl by dw, correct? And as we saw, this can be split into dl by dy into dy by dw. So dy by dw means taking the derivative of this with respect to w. And if you do take the derivative of this with respect to w, which is dy by dw, and if you apply uh, the chain rule, what you will get is, first you will do ReLU dash dot dot dot, and there will also be a term where you just have to multiply it by the ReLU. So remember that, let's say, when you take the chain rule, then gradients are of course something which you need to find, but you also need to multiply by that actual function itself. Whatever is the case, if you are in this side of the ReLU function, everything will be zero. Like this ReLU dash will be zero because it's constant, the gradient is zero. ReLU also will be zero because it's just a flat line over here. So this entire derivative will become zero. This again means that there will be no updates to that particular weight from this neuron. So if one neuron starts receiving negative weights, then the weights corresponding to that particular neuron will never update, because now it is producing. So if the weights are negative, okay, then the output of the neuron will be in this area. So the derivative will be zero, the output will also be zero, so the weights will not update. So the weights will again be negative, so that the output is negative. So this problem will never update itself. So we are stuck. Let me try to explain it again. If the weights coming into a neuron are such that the input to the neuron is negative, then then the ReLU output is negative, the gradient is also negative, which means the weights won't update. The weights will remain fixed for all the iterations, which means that particular neuron is now serving no purpose. It is essentially dead. So this is also called as the dead neuron problem. This is called as the dead. This is also called as the dead neuron problem. And this is faced by ReLU. So if the input is negative, then sometimes that neuron weights, they stop updating themselves. So essentially that neuron then becomes useless to us, because nothing is changing in that particular neuron, and the output also is given to be zero. So the output coming from that neuron is also zero. So that neuron is completely useless, it's dead. If it's producing some kind of an output, then at least we can say that something is happening. But even it's not producing any output also, because not only is the derivative zero, but even the output is zero if we enter this negative part. So we might as well remove that neuron. So that's why this is called as the dead neuron problem, and this is one disadvantage of Relu. But it's not. It turns out that for solving big neural network problems, it's not too much of an issue, because even if some neurons become dead, there are huge number of other neurons to take care of the problem, and their weights are continuously updating. And it turns out that the advantages provided by Relu are much greater than the disadvantages. The first advantages, as I told you, is that its gradient does not vanish for positive x. That's amazing. The second advantage is that if you look at sigmoid, we have to find this exponential. It's 1 upon 1 plus e raised to minus x. Correct? Also, if you look at tan h, tan h is 1 upon 1, sorry, it's 2 upon 1 plus e raised to minus 2x minus 1. In both of these functions, we have to find an exponential operation, right? And as the number of inputs, number of neurons increase, this takes a lot of computational time, and it's computationally expensive. Whereas if you look at Relu, it's very simple, right? It just x equal to y for the positive x, and for negative x it's 0. So it's very computationally efficient, and that's one of the big advantages of Relu. And let me just write it down here. Relu has a faster training. Relu has a generally faster training than Tan H and Sigmoid. Also, this depends specifically on the problem, but as a general rule, since Relu does not have complicated exponential operations, if we take a problem which has huge number of data points and lot of neurons, training a Relu is generally much faster. So due to these advantages of faster training, lower or no vanishing gradient problem, Relu is really preferred uh, over TANH and Sigmoid, especially for regression-oriented tasks, and sometimes even for some layers of or some layers in classification tasks as well. In classification, the output still has to be Sigmoid, but other layers can be Relu. Okay. So one more advantage of Relu is that in regression, the output is not in regression. We don't need the output to be between 0 and 1 and minus 1 and 1, right? So in regression tasks, tanh cannot be used and sigmoid cannot be used. So Relu is preferred because it has no limits. It can take any y, especially for positive x. So for Relu, the output is not in a specific range, and so that is also an advantage. So output not in specific range, which is a good thing for us, especially for regression tasks. Now, I told you about this dead neuron problem, right? In the dead neuron problem, if we are on the negative side, then the gradient becomes zero and the output is also zero. So to fix this, people developed one more activation function, um, which is the fourth activation function which we are going to look at today, and that's called as the leaky relu. So the leaky relu looks like this. So let me first draw it for you. On the positive side, it's exactly similar to Relu, and on the negative side, we just add a small slope so that instead of it being a constant zero, it's like this straight line. So mathematically, the leaky Relu looks like this. Um, y is equal to, or f of x is equal to x if x greater than 0, and ax if x is less than 0. And this a is sometimes most of the times it's a very small value, like it's 0.01, etc. That's why the slope of this line on the negative side is much lesser than the slope on the positive side, which is y equal to x. So you see how this will solve the dead neuron problem. Now, if you take a look at this particular side, even if the weights and the inputs feed into this ReLU such that it's negative, let's say the input to the ReLU is negative, the output won't be zero. The output will be a small negative value. Even the derivative won't be zero. And so if we find the derivative of y with respect to w, this won't be zero. So the derivative of loss with respect to w will not be zero. So the weights will continue to update themselves. And this will solve the dying neuron problem. So this leaky Relu solves the dying neuron problem, and that's why it's preferred for applications which are getting stuck in local minima. So this is the fourth activation function which we saw. The fifth activation function is one highly famous and a very popular activation function, and it's called as the Softmax. It's called as the Softmax activation function. So the softmax activation function is typically used for multi-class classification problem. So let's say we looked at cats and dogs, right? And we are predicting whether it's a cat or a dog. But let's say there are 10, or rather there are 5 animals. Let's say there is a cat, there is a dog, there is a horse, there is a rabbit, and there is an elephant. Let's say there are these 5 animals, and we want to have an activation function at the final layer which can give me that which animal or my neural network will classify which animal with the highest probability. So what is the output most probable to be? Remember, the sigmoid is only for binary classification, cat or dog. But if we want a multi-class classification, we need a different function, and that's why the softmax came into existence. So let's say the output of the final layer was something like this: 1.3, 5.1, 2.2, 0.7, and 1.1. These are some numbers which are kind of representing how likely is it to be a cat, dog, horse, rabbit, or elephant, right? Now, what I want to do here is I want to convert this into a set of probabilities. So this is clearly not a probabilities, right? Because first of all, they don't lie between 0 and 1. Secondly, they don't add up to 1. I also need these probabilities to add up to 1, so that I can say that there is a probability or 50% probability of it being a dog, 40% of it being a cat, 2% horse, 6% rabbit, and 2% elephant. So I want the probabilities to add up to 1, and I want the probability for each particular class to be between 0 and 1. So how do I do that? We use a mathematical operation in the middle, and that's called as the softmax. So for the sake of representation, let me denote this as x1, this is x2, this is x3, this is x4, and this is x5. So instead of just having x1, x2, x3, x4, x5, the softmax function is that why don't we replace every quantity by e raised to, let's say for x1, e raised to x1 divided by sigma of e raised to xi, which is basically saying that x1 will be replaced with e raised to x1 divided by e raised to x1 plus e raised to x2 plus e raised to x3 plus e raised to x4 plus e raised to x5. Then this x1 will be replaced by this. Similarly, x2 will be replaced, and similarly x5 will be replaced by e raised to x5 divided by e raised to x1 plus e raised to x2 plus e raised to x3 plus e raised to x4 plus e raised to x5. First thing you should see is that all of these quantities e raised to x1 divided by this will lie between 0 and 1, because the denominator is always greater than the numerator, and all these quantities will be positive because the exponential operations are positive. So the first thing what I told you, that each of these quantities should lie between 0 to 1, because we want to describe them as probabilities, that's taken care of. Now let's look at the second one. If you add if you add the first term, second term, third term, fourth term, fifth term, you will basically get that the summation is e raised to x1 plus e raised to x2 plus e raised to xe plus e raised to x4 plus e raised to x5. This is adding up the numerators, and the denominators is anyway e raised to x1 plus e raised to x2 plus e raised to x3 plus e raised to x4 plus e raised to x5. That's fixed. So we can see that this sums up equal to 1. So essentially, instead of writing them as x1, x2, x3, x4, x5, if I encode these numbers using this mathematical representation, I can see that they lie between 0 and 1. And secondly, they all sum up to 1. This is a great indication that they can be considered as probabilities. Now let me show you how this particular matrix transforms. So my current matrix was 1.3, 5.1, 2.2, 0.7, and 1.1, right? When I apply the softmax operation which I explained to you above, these numbers will transform to the following: 0.02, 0.90, 0.05, 0.01, and 0.02. Now what this means, so let me also write down the animals: cat, dog, horse, rabbit, and elephant. So cat, dog, horse, rabbit, and elephant. What this essentially means is that I have 90% confidence or probability that it's a dog, 2% that it's a cat, 5% that it's a horse, 1% that it's a rabbit, and 2% that it's an elephant. That's amazing, right? That tells us so many things just instead of just this. Now we have a perfect representation in terms of probabilities. Second thing which a softmax does very nicely is that if you look at these two quantities, 5.1 and 2.2, they're kind of close, right? 5.1 is greater than 2.2. But I'm not that confident that okay, dog is higher than a horse. But if you do the softmax, there becomes a huge difference between the dog and the horse. This 5.1 and 2.2 translate to 90% probability of it being a dog and just 5% of it being a horse. This is what Softmax does. It encourages the model to be more confident about its best predictions, and it encourages it to be very less confident about its not so good predictions. So it kind of makes me more confident as a user to say that okay, my model does well now because 90% confidence it's saying it's a dog. Whereas if I just look at these two numbers, they're kind of close, so I'm not really sure how well my model is doing. So remember, Softmax encourages my model to be more confident about its good predictions and discourages the bad predictions or makes them less confident. Why is it called as Softmax? Because if you take the max operation, if you take the max operation, it directly outputs the maximum. So if you take the max operation on this data, it would have given just 5.1. What Softmax does, the lower probability things, if you take the lower probability values, it does not directly discard the lower probability. That's why it is a max which is soft. And that's why actually it's called as soft max. When you are doing a multi-class classification such as the one which I explained here, or for any multi-class classification where you want to represent the output as a set of probabilities, softmax is the most commonly used and very much preferred uh, activation function. The only disadvantage of softmax which I have personally come across is that softmax is quite computationally expensive. So the disadvantage of the softmax algorithm is that it's quite computationally it's quite computationally expensive, and you can already see it, right? We have to take multiple exponential operations, and then we have to convert all inputs to these exponents, That's why it's computationally expensive. But other than that, it's a brilliant way to encode outputs as probabilities in the final layer. The last activation function which we are going to look at is something called as the swish. And the input output representation for the swish activation function is y is equal to x into sigmoid of x. And if you plot this particular activation function, it looks something like this. Um, it looks something like this. So this is x and this is y. So here, as you can see, the sigmoid was stagnating, right? But this does not stagnate. So it solves the vanishing gradient problem. That's one advantage. Secondly, it's not bounded, so it does not lie between 0 and 1. So it's very much used in regression tasks. So these are the two advantages of the Swish activation function. It's not used very commonly. It's not used as commonly as let's say Softmax or Relu or Tanh or Sigmoid. But it's an activation function to keep in mind in case none of the activation functions are working for your specific problem. Sometimes Swish has worked for me. Okay. So in the next part of this lecture, I will just have a small section on why non-centered activation functions have a problem in back propagation and why it's better to have centered activation functions. And we'll also look at which activation functions to use for which type of problems. So the last thing which I want to cover is non-centered activation functions and what are the problems which they can lead to. This is a small topic and it's kind of a detail, but I've seen this question being asked in interviews sometimes, so it's better to clarify this. So first of all, what is meant by centered activation and what's meant by non-centered, right? So if you look at sigmoid, the sigmoid looks like this, right? And it goes from 0 to 1. If you look at relu, the relu looks like this. So these functions are not centered around x equal to 0 because they are always positive. A centered activation function will look something like the tan h. So if you look at the tan h, this is centered around x equal to 0, right? So this is sigmoid, this is non-centered, this is relu, which is non-centered, and this is tan h, which is centered. So it has positive values as well as negative values. So it's centered around the origin. When I say centered, I should clarify it is non-centered around origin. Okay, now what are the problems which this would have? Uh, let's say we are using the sigmoid, okay, and these are the neurons and I've used the sigmoid, so the output will be the output of the sigmoid. So let's say this is x1, x2 and x3, and let's say all of these x's are feeding into my next neuron. And since we are using sigmoid which is non-centered, all of these x's will be positive, all xi will be positive, correct? And all of these are feeding into my neuron like this. Now let's say this particular neuron just has the identity activation function, so it's like it just sums up the weights. So if you want to find the gradient of the loss with respect to wi, this will be gradient of loss with respect to f into gradient of f with respect to wi, and gradient of f with respect to wi is just xi. So this is gradient of loss with respect to f into xi. Now let's say this is fixed for that particular iteration, okay? For since all the xi's are positive, as we have seen here, all the gradients with respect to loss will also be positive. So gradient of loss with respect to w1 will be positive, gradient of loss with respect to w2 will be positive, gradient of loss with respect to w3 will be positive. So all the gradients of the loss with respect to all the weights will be positive, and this is a problem for us. If all the gradients are positive, then this is a problem because it leads to a kind of pattern which is called as the zigzag pattern in back propagation. And let me explain to you how this looks like. So let's say if we have two parameters, So let's say we have two parameters, W1 and W2. Let's say these are the two parameters. So if the gradient in two dimensions, if the gradient in two dimensions is always of the same sign, so is always positive, so is of the same sign, let's say, is of same sign. So let's say always positive or always negative. Uh, then we can only move north, northeast, or southwest. Why? Let me explain this to you. So let's say this is the particular point, okay? Northeast direction is this, which means that the gradient, so this is the, so this is, let's say, the, so the x-axis is gradient with respect to W1, and let's say y-axis is gradient with respect to W2. Let's say both are positive, which means that if we look at the xy plane, we can always move in this direction, only this direction. Whereas if both are negative, we can only move in this direction. We can never move in this direction, in this direction. Why? Because if we move in this direction, it would mean that dl by dw1 is greater than 0, which is good, but dl by dw2 is less than 0, which is not the case. So we cannot move in this direction. What about this direction? If we move in this direction, then dl by dw2 is greater than 0, which is good, but dl by dw1 will be less than 0 since it's in this way, it's in the left way. So we cannot move here also. So we can only move in the northeast direction or the southwest direction. Now I'll show you how this leads to the zigzag pattern. So let's say this is the W1, W2 space. So if we are starting from this point, and let's say this is our goal, ideally when we optimize, we should be able to move in this way, right? But see, this direction is restricted to us because all the both the gradients are positive. So then we'll have to make these kind of patterns. We can only move in northeast or southwest, so we can only move in this direction or this direction. So you have to move here, then come here, come go here, come here, go here, come here, and then we have to reach your goal. And that is the zigzag pattern of back propagation in this case. So this is the problem which happens if gradients are all of the same sign. So if we have the sigmoid activation function or the Relu activation function, these outputs are always positive, right? So all the xi's will be positive. So the sign of DL, sign of gradients will be determined by xi. So if all xi's are positive, the gradients will always be positive, and that's the problem for us. It will again lead to the same zigzag pattern. That's why it's preferred to have a centered activation function such as the tan h. So if you look at the tan h activation function, tan h actually takes positive values as well as negative values, and that is good for us because let's say if we look at the derivative of loss with respect to weights, there is this xi here. So if xi is positive, then this will be positive. If xi is negative, then this derivative will be negative. So for some weights, the gradient of loss with respect to w might be positive and for some might be negative. So when we are about to move uh, based on the gradient of the loss with respect to weights, we can move in all these four directions here. And so in this case, we can directly go from our start to the goal and we won't have to follow the zigzag pattern. That's why the tan h activation function does not have these problems because it's a centered activation function. It goes from +1 to -1. Sigmoid and Relu, on the other hand, are non-centered activation functions. And that's why they have problems in back propagation. So now let us come to the final section of activation functions where we will look at for a specific type of problem, what is the activation function which is to be used. So I am going to be looking at three problems especially here. The first is regression. The second is a two class classification problem. And the third is a multi-class classification problem. multi-class classification. So if you are watching this video, first I would encourage you to pause for a while and think about, based on what all we have learnt in this lecture, the six different activation functions: Swish, Softmax, Relu, Tanh, and Sigmoid. Which is the activation function which you will use for these different tasks? Okay, so now let us start looking at the answers here. So for the regression, so let me write down these six here. So Sigmoid, Tanh, Relu. So I'm not liking writing Leaky Relu here. I'm just writing Relu. Then Softmax, and I'm also not writing Swish because it's not commonly used. So we'll be looking at these four activation functions and which one to use. Okay, so the first task is regression. Sigmoid and Tanh are bounded. Sigmoid is bounded between 0 and 1. Tanh is bounded between -1 and 1. So they are not the best activation functions to use for regression because we don't need bounded outputs when we are dealing with regression problems. The output can be finite numbers ranging up to infinity. Uh, we also won't use the softmax because softmax is typically used for a classification problem. As a result, for relu for regression, either we use an identity activation function, which means that y is just equal to x, which is also pretty commonly used in regression, or we use relu activation function in regression. For the two class classification, we won't use sigma. Sorry, we will use sigma for the two class classification. It's the most preferred activation function, and we can also use tanh for the layers before the final layer. So typically, what is done in the two class is that tanh, and finally you have the sigmoid as the activation. So I'm going to be writing here a combination of tanh and sigmoid for the two class. For the multi-class classification, the only best option out of these four is the softmax activation because it's predominantly meant for solving multi-class classification problems. So these are the types of activation functions which you can use for these different types of ML problems. Remember that there are a number of things which we discussed today, such as the vanishing gradient problem, the dead neuron problem, then centered versus non-centered activation, and all of these things play an important role in deciding the activation function in the first place. We did not discuss about the identity activation function, but it's pretty commonly used in regression tasks. Sometimes it's much better to use the identity instead of using a wrong activation function. So that brings us to the end of this particular lecture where we learned about six different activation functions, starting with Sigmoid, then Tanh, then Relu, Leaky Relu, Softmax, and Swish. We looked at the vanishing gradient problem faced by Sigmoid and Tanh. Then we also saw the dead neuron problem which Relu faces, and we saw how Leaky Relu solves that. We saw how Relu does not have the vanishing gradient problem, whereas Sigmoid and Tanh have that problem. And finally, we looked at softmax and how it's an amazing activation function for a multi-class classification. So thank you everyone, and I'll see you in the next lecture.